If there is one basic task in electronics, one most critical skill to be mastered, this is it: soldering. To most people, soldering is a very simple thing. A hot iron and a little solder, that's about it. If we're just soldering a couple of pipes together, well, maybe. But soldering printed circuit boards, that's another matter altogether. Today, soldering has reached the level of a fine art, and it's become a vital one in many fields.
It came into its own with the space age, when incredible amounts of raw power had to be put under precise electronic control. Everything depended on how reliable every one of these little soldered connections were. High reliability is what spelled ultimate success or failure. And it was not only for ventures like this. It had been demanded in many other settings as well. Anywhere that information was vital, when human lives depended on it, and there was no room for failure.
Roger, Denver, with 41,000 feet.
Today, all of us depend upon and expect high reliability. It's no longer just in the very sophisticated systems like this one.
Okay, thank you. American 178, contact Los Angeles Center, 128.8, good day.
We now find it everywhere, in the common things we count with, in the computer systems of business and government, and in all the kinds of consumer goods that incorporate electronic circuits.
Your dial is set at 780.
They've become part of our everyday life, and we expect them to work right.
With all of them, a basic procedure is the making of a reliable solder connection. And how to do it is what you're about to learn. We're going to watch an expert go through all the basic techniques you need to know, and then you'll have a chance to practice them on your own materials. Let me show you what we're going to cover. First, we'll take a look at solder itself, the basic material in the process, and we'll see what it contains. We'll also find out about flux, what it does, and the proper kind to use. We'll cover what actually happens when you solder, the meaning of wetting action, and the necessary role flux plays in removing oxides. And soldering irons. You'll learn not only how to match them to the job, but also the many factors other than just tip temperature that affect how fast heat gets into the work. You'll learn what WPI stands for, one of the secrets of real craftsmanship. And you'll learn how to recognize good solder joints and bad ones, what makes them acceptable or unacceptable, and what are each of the characteristics of the preferred solder joint. The components we'll be working with are the ones you'll encounter in today's electronics, on both single and double-sided circuit boards, with various types of terminals and connecting wires. After we watch how to solder each one of them, then you'll do it, developing professional skill as you go along. And for your permanent reference, we have a student's handbook available. It provides further detail on each of the topics we're going to cover. So let's begin, and we'll start with the process itself, connecting two pieces of metal together to form a reliable electrical path. Why solder them in the first place? We could put them together with nuts and bolts like this, but then we've got two problems. First, we can't be assured of a good contact to begin with, and then later, vibration will probably work it loose. Second, oxidation or corrosion will be continually occurring on the surfaces. This will progressively decrease the electrical conduction between the two. A soldered connection does away with both of these problems. There's no movement and no surface to oxidize. We formed a continuous conductive path from one to the other. What makes it possible are some very unusual properties of solder itself. So let us look at how it's made. Solder is a metal alloy made by combining tin and lead in different proportions. Here, the proportions are equal, so it's known as 50-50 solder, 50% tin and 50% lead. A 60-40 solder would consist of 60% tin and 40% lead. You can find these percentages marked on the various types of solder available, and sometimes only the tin percentage is shown. The striking fact about solder is its low melting point. Pure lead has a melting point of 620 degrees Fahrenheit. Pure tin, a melting point of 450 degrees. But when you combine them into a 50-50 solder, the melting point drops to 420 degrees, lower than either of the two metals alone. And other ratios of solder have their own particular melting points. With most combinations, melting does not take place all at once. 50-50 solder begins to melt at 361 degrees, but it's not fully melted until the temperature reaches 420 degrees. Between these two temperatures, the solder exists in a plastic or semi-liquid state. Some of it, but not all of it, has melted. The plastic range is different for other combinations of tin and lead. With 60-40 solder, the range is much smaller than it is for the 50-50. And here is a special case, the 63-37 ratio, known as eutectic solder. It has practically no plastic range and melts almost instantly at 361 degrees. The most commonly used solder in electronics is the 60-40 type. But because of its plastic range, you need to be very careful and not move the lead during cool down, which causes a disturbed joint looking like this one. Notice that the solder has a rough, irregular appearance and looks dull instead of bright and shiny. It's one of the types of unacceptable joints that we'll see in a few minutes. Under some circumstances, minimal heat may be desired, and it may be difficult to maintain stable leads during cooling. This is where eutectic solder is used, since it cools very rapidly from a liquid to a solid state. To someone watching the soldering process for the first time, it looks like the solder simply sticks the metals together, like some hot melt glue. But what actually happens is far different. As the hot solder comes into contact with the copper surface, a metal solvent action takes place. The solder dissolves and penetrates the copper surface. The molecules of solder and copper blend together to form a new metal alloy, one that's part copper and part solder, with characteristics all its own. This solvent action is called the wetting action. Wetting can only occur if the surface of the copper is free from dirt and from any oxide film that forms when the metal is exposed to air, and the solder and work surface have to have reached the proper temperature. This copper plate looks clean, but there is a thin film of oxide covering it. When you apply solder, it acts like a drop of water on an oily surface. The solder does not come into contact with the copper. No solvent action takes place, and the solder can easily be removed. To have a good solder bond, the oxide must be removed and prevented from occurring during the soldering process. For this, flux is used. When it melts, it will remove the thin film of oxide. The solder now flows, and the wetting action can take place. When the metal cools, it is a solid mass, one that is mechanically and electrically continuous and cannot be scraped off. Many types of flux are available, in paste and liquid form. The fluxes used in electronic work are basically rosin in a modified form and may contain mild activators in some cases to accelerate their action. When flux is cool, it is relatively non-corrosive and non-conductive. But when heated to its melted state, it then becomes sufficiently active to remove all the surface oxides and carry them away during soldering. Many of the types of fluxes available have an acid base and should never be used for electronic repair. They remain corrosive at all temperatures. Fluxes containing zinc chloride are acid fluxes and should not be used. These fluxes are excellent for their intended use, but they have not been designed for use in electronics. Acid core solders are also available and should not be used in electronic work. Rosin fluxes, although they're relatively non-corrosive when cool, should still be removed with a solvent after soldering. This prevents their sticky surfaces from collecting dirt and moisture. Combinations of solder and flux are in wide use today. They're available in a variety of solder sizes and percentage of flux, and they have the advantage of automatically controlling the ratio of flux to solder. The concepts we've just covered are very important and are fully presented in your handbook. At this time, your instructor will review the material with you, present particular specifications, standards, and practices of your organization, and have you note them in your handbook for a permanent record. In any kind of soldering, the primary requirement, beyond the solder itself, is the use of heat. You can apply heat in a number of ways, but here we're concerned mainly with just one of them, the conductive type of soldering iron. These irons come in a variety of sizes and shapes, and you need to choose the right one for the job at hand. If we took an inside look at the basic iron, we'd see that there are three main elements: a resistance heating unit, the heater block, which acts as a heat reservoir, and the tip or bit for transferring heat to the work. In the basic iron, the input voltage is fixed and constant, so the resulting tip temperature depends on the capacity of the heating unit and on the mass of the tip and block. More elaborate irons incorporate ways to vary the temperature of the tip. In this type, the operator can increase or decrease the voltage across the heater and consequently vary the tip temperature level. Another type of iron incorporates a temperature-controlled magnetic switch inside the block. The switch is activated by a small magnet. As the magnet is attracted to the heater block, it closes the switch and the iron heats up. At a predetermined temperature, the magnet loses its magnetic properties and the switch springs open. Then, as the iron loses heat, the cycle repeats, resulting in a set maximum tip temperature. Still another variation is this type of iron. A temperature sensor has been built within the block. The operator sets the desired temperature, and then through a closed-loop feedback system, the power to the resistance heater is turned off and on to maintain the tip at the desired temperature. There are many arguments for and against each of these types of irons, but controlling tip temperature is not the real problem. The real problem is controlling the heat cycle of the work. How fast the work gets hot, how hot it gets, and how long it stays there. This is affected by so many other factors that in reality, tip temperature is not that critical at all. The first factor to consider is the relative thermal mass of the joint. Let's start with a single pad on a single-sided board. There's relatively little mass here, so the pad heats up quickly. If we now move to a double-sided board with a pad on both sides of the hole, we have twice the mass we started with. Then, if we make the hole a plated through one, we'd have an even greater mass. And that's before the component lead goes in. Lead mass can vary quite a bit. Some leads are much bigger than others. And that's not all we have to consider at any particular joint. Suppose we mount a turret terminal here. Again, the mass greatly increases. And now we add one wire or two. The mass is greater still. Each joint, then, has its own thermal mass. And how this combined mass compares with the mass of the iron tip determines the temperature rise of the work. In this situation, we have a large work mass and a small iron tip. Temperature rise will be slow. If we reverse the situation, putting a large iron tip on a small work mass, then temperature rise of the work is more rapid, even though the temperature of the tip is the same. We could go a step further and consider the capacity of the iron itself, its ability to sustain a given flow of heat. Let's look again at the basic iron. Irons are essentially instruments for generating and storing heat, and the reservoir is made up of both the block and the tip. The tip is removable and comes in various sizes and shapes. It's the pipeline for heat flowing into the work. For small work, a necked-down tip is used so that only a small flow of heat occurs. For large work, a large tip is used, providing greater flow. The reservoir is replenished by the heating element. But when an iron with a large tip is used to heat massive work, then the reservoir may lose heat faster than it can be replenished. This is where the size of the reservoir comes in. A large heating block can sustain a large outflow longer than a small one can. Another way to increase the iron's capacity is to add more heating element, and in that way increase the wattage of the iron. These two factors, block size and wattage, determine the iron's recovery rate. So if the job requires a lot of heat, you need not only the right temperature, but also the right size tip, an iron with a large enough capacity, and one that can recover fast enough. Relative thermal mass, then, is a major consideration for controlling the heat cycle of the work. A second factor is the surface condition. If the pads and leads are covered with oxides and other contaminants, they create a barrier to the flow of heat. Then, even though the iron tip is the right size and temperature, it may not be able to put enough heat into the joint to melt the solder. The tinned iron tip can be kept clean by wiping it on a wire brush before each use, and then shocking off the remaining oxides on a wet sponge. The work is always wiped clean before soldering, with a solvent such as trichloroethane or isopropyl alcohol to remove any grease or oil. Remember that you can't create a good solder joint on a dirty surface. After surface condition, there's a third factor to consider: thermal linkage, the area of contact between the iron tip and the work. Let's look at the situation in cross-section with the iron tip touching a round lead. The actual contact occurs only at this point, so the linkage area is very small, not much more than a straight line along the lead. We can improve things a great deal by putting a small amount of solder right here. Now the linkage area looks more like this, and heat flow will be much faster from the iron tip. So now we've seen that there are more things than just the temperature of the iron tip that affect how quickly the joint is going to heat up. It's become a complex control problem with a number of variables to it, each influencing the other. And what makes it so critical is time. The general rule is, for high reliability soldering, apply heat for no more than 2 seconds. Any longer than this, and you'll begin to damage the board. With all these factors, the soldering process appears too complex to accurately control in so short a time. But there is a simple solution to it all, and the secret is right here. WPI, Workpiece Indicator. When you know how to use workpiece indicators, you know one of the secrets of craftsmanship. Put simply, workpiece indicators are the way the work talks back to you, the way it tells you what effect you're having, and how to control it so you accomplish what you want. Sound is the workpiece indicator on this job. More often, workpiece indicators are visual ones. And sometimes you may use the sense of touch. In any kind of work, you become part of a closed-loop system. It begins when you take some action on the workpiece. Then the workpiece reacts to what you did. You sense the change, and then modify your action to accomplish the result. It's here in the sensing of the change, by sight, sound, or touch, where the workpiece indicators come in. For soldering and desoldering, a primary workpiece indicator is heat rate recognition, observing how fast heat is flowing. A tip like this is too big and too hot for the work. The heating rate is so fast, you can't control it. This tip is too small for the work. What you see is a mush kind of melt. The heating rate is too slow. When the right tip size and temperature are used, then the heating rate is correct. Heat rate recognition, then, is our workpiece indicator for high reliability soldering. It makes a complicated problem of control very simple. Just watch and see how long it takes the solder to melt at the joint. It should melt within 2 seconds. If it takes any longer than that, you're increasing your chances of damaging the board. Board damage comes mainly from heat. But it's not only the heat that does it. It's heat combined with pressure. Let's look at a model of a circuit board and pad. When a hot iron tip is applied with a light touch, there's no damage. And it can be done repeatedly. But now, if pressure is also applied, this is what happens on the surface. The reason why can be shown on a graph. As the materials are brought up to solder melt temperatures, 80% of the bond strength between pad and board may be lost. In practice, remember to use a light touch. No more pressure than you'd get from the weight of a pencil balanced on its point. Push down on it like this, and you may lose the pad. A general rule for preventing overheating is to get in and get out as fast as you can. That means using the hottest iron you can react to. one that gives you a 1 to 2 second dwell time on the particular joint you're soldering. In the next part of the program, we're going to take up turret terminals and begin to apply what we now know about high reliability soldering.